Maybe then I'll be privileged to introduce the speaker. Um, is Trevor holding up a message for us? I can't see. His picture's too small. No? All right. Okay, yeah, let me try again. Yeah, okay, so we're pleased to welcome Alessio, who will talk about order polytopes of graded polytopes are gamma effective. Please go
Thank you,
ahead.
Graham, and thank you to all the organizers for giving me the opportunity to talk here. I really like the BFT seminar. I've been trying to attend as much as possible, even though it's an online format. So I'm really glad for this opportunity. So the title of my talk is Ordered Polytopes Graded Posets are Gamma Effective. And as always, I'll try to, my talk will be basically trying to explain the title. So feel free to interrupt me whenever needed. I'm not sure I can see the questions, but feel free to open your mic and just talk. So I will start by some problem that has already been settled, but that kind of is the starting point for our project. By the way, this is joint work with Akihiro Higashitani from Osaka. So I want to start by talking about p omega partitions and the Neggers-Stanley conjecture. So this was a hot topic from the 80s all the way to the early 2000s when this conjecture was disproved, even though there is still some open cases to wrestle with. And so let's begin and see what a p omega partition is. Well, first of all, P is going to be a finite poset here and in the rest of the talk, basically. And then I'm going to have omega is going to be just a labeling of the poset, of the vertices of the poset, by numbers from 1 to p. So it's a vertex labeling. Okay, so what is a p omega partition? It's nothing but a map from the vertices of the poset into natural numbers bigger than 0, such that two things happen. The first one is just that sigma is order reversing. So this first condition has nothing to do with omega. It's just something about the poset itself. So I want that whenever this happens, then I get the opposite inequality. Why the opposite one would be a good question. I don't really have a good answer for that. It's something, depending on the author, you can find both conventions, but I think that in this particular setting, it's usually the order reversing business. So that's for the first one. What does omega do? What is the information that omega gives us? Well, sorry. If it happens that you have a pair of elements that lie one below the other, but are such that this happens, so you basically get the wrong labeling, sorry, the wrong inequality, then I want sigma to be a strict inequality here. So here there was there used to be a bigger than or equal to. In this case, it's just a strict inequality. Okay, so that's what a p omega partition is. And then you can count these. And so this would be the number of p omega partitions. And I want just to fix the codomain and say, well, I cannot use numbers that are larger than some n. So I'm going to say that the codomain is 1, 2, 3, n. Okay, and it can be proved that this thing is a polynomial in n of degree the cardinality of the poset. And this is what is known as the order polynomial. of P and omega. And if this screams Ehrhart counting to you, you would be right in the sense that we are going to see how to interpret these results in a polytopal setting soon. So for now, we just have this thing that would be, like in the analogy, the Ehrhart polynomial of some object. And then if I have an Ehrhart polynomial, I kind of expect to get an H star polynomial as well. So for those of you who are not familiar with this notation, what I mean is just that I can express, well, one can find, let's say, another polynomial that I'm going to call W, because that's the name that it has in this particular theory. And I'm going to call it W of P omega T. And I can get that by imposing that this holds. So I'm going to use these as coefficients of some generating series. I need to shift everything by one, just, because I had basically 1, 2, 3 instead of 0, 1, 2 in the counting. So that's not really any problem. So I'm going to have n plus 1, but then t to the n. And if I write these in a rational fashion, then this is what I get. So I can find this new polynomial up here. So now I've got all the ingredients that I needed to state the conjecture. So the conjecture that was originally due to Neggers and then was generalized by Stanley is that whenever I have a labeled poset, P omega, this new polynomial is real rooted. It was a very reasonable conjecture and it stood for quite a while. However, it's false, so it was disproved. And it was disproved in several papers, just because of basically different levels of generality. So the main papers I'm thinking of are a paper by Peter Brändén and another one by John Stembridge. And if you're curious, I can just draw a couple of examples of posets where things go wrong. A very easy one is basically two chains. I'm drawing the Hasse diagrams here. And then I have this edge. So this thing is a counterexample. However, you could say, well, I don't particularly like this example because there is clearly an edge where omega plays a role in the sense that there is this 12 that is lower than 11. So one would say that the labeling is not natural in the sense that it is not compatible with the partial order that I'm given. So if you're happy with this non-natural labeling, this is a counterexample. But you could also find a natural counterexample. You just need to draw something larger. And I'm gonna try, but I'm not sure I'm gonna draw it very well, but whatever. So yeah, pretty much. So this is 1, 3, 5, and then I go up like this. And then on the other side, I got 16. I should have been a little lower with this. Sorry. No, this was wrong. So I'm just copying the example here, but it's not so important. I just want to say that there is some natural naturally labeled poset. this would be 13. Then I have this one, and I think I'm done. So yeah, apologies for this, but if I drew it a little better, you would see that this is actually natural. I tried to draw it in a way, such a way that the numbers are actually respecting the order. And you see,
Yeah.
sorry?
Can I ask if the numbers like 11, 22, 17, 16, are those special, or is this like more of the structure of the posets?
I don't really know because I was looking up these examples because they were in some survey, and I know that the smallest example I know about, which is not natural, is on 10 vertices, and it's actually pretty nice. I mean, you could draw it, and it's a bit nicer than these. And both this and the first one are due to Brändén. This middle one, I think it's the smallest. I don't think you can do any better than 17 vertices for some reason. And this one was definitely found by Stembridge. So this one was found sometime after Brändén produced his examples. I think it was some combination of computer search and maybe it was a not exactly brute force, but directed in some way. But I don't know exactly why this should be the example.
Thank you.
Yeah, thank you. Okay, so it looks like, well, the conjecture itself does not work. However, there is still something that could be true. So, sorry about the handwriting. I'm just trying to get used to my iPad. So, recall that a finite poset P is called graded, and here I'm gonna state one of the two possible definitions of a graded poset. So for my talk, graded means that all maximal chains have the same number of edges. Okay, so if P is graded and naturally labeled, which is what I was mentioning before, so it means that if P is smaller than Q, then omega of P is smaller than, smaller than omega of Q. If this happens, then the order polynomial, the W polynomial is palindromic, so it's symmetric. And this opens the way to studying not just real rootedness, but also gamma-nonnegativity and all, unimodality you could try also without palindromicity. But when a polynomial is palindromic, I'm going to say it here, you have real rootedness, you have unimodality all the way here, and one would imply the other, but there is some property in the middle, which is called gamma-nonnegativity. And I'm going to just demonstrate it by an example. So what it means for a polynomial to be gamma-nonnegative, for instance, say that your polynomial is, I don't know, something like that. So these are my coefficients. I'm just going to write them like this. Now what I want to do is the following game. I'm just going to write down lines of the Pascal triangle. So in this case, I start by 1, 4, 6, 4, 1. And then I see what's left. So what is left is, well, now we need to go with multiples of 1 to 1. Let's say, well, let's try it with this one and see what happens. So in this case, I have 1, then I settle the 5, so that's fine. Then it's an 8, so I need 3 more copies here. This thing I found on the diagonal is my gamma vector. So in this case, I found just positive numbers. Well, that's not always the case, of course. If I wrote something like 1 plus 3t plus whatever, I would have needed a -1. So gamma-nonnegativity means exactly that if you take the coefficients of your polynomial, of your palindromic polynomial, and you play this game, you get an positive integer vector. If that happens, your coefficients are unimodal, and if your polynomial is real-rooted, you get this property for free. So it's kind of some middle ground in a sense. So why do we care? Well, for these graded posets, it was proved by Reiner and Welker. Even though it was published in 2005, it was, well, the archive version is from 2002. If P is graded and naturally labeled, then the omega polynomial is unimodal. And then, again, Brändén, in another paper, that is the one we are using the most for our paper with Akihiro, he proved that under the same hypothesis, you can say more. You can say that this object is actually gamma non-negative. And I know what you're thinking, well, could it be real-rooted? After all the examples I showed you before, they were not graded in our sense. And to the best of my knowledge, this is still open. So if P is graded and naturally labeled, I don't think it's known, or at least I didn't find it in the literature, and other people confirmed this to me. So it's not really clear whether we do get real-rootedness here. And this will not be solved by the end of the talk, if you're wondering about that. So I would like to know the answer to this, but I wouldn't know how to tackle that. Okay, so what did Brändén do to actually prove the gamma-nonnegativity result? Turns out that there is a lot of nice combinatorics that you can do in this context. And so, first of all, even though the result is about graded posets in this context, he introduced a larger class that is actually more suitable. It's a bit more general, and you can prove nicer statements about those. So, to prove his result, Petter introduced a new class of posets that are called sign-graded posets. And actually, the statement I gave you before would work for any sign-graded poset, not just for the usual ones. Okay, so what is that? I'm going to state this in terms of edge labelings instead of vertex labelings. You can do the translation if you are in the right hypothesis. So assume that you have some edge labeling by ones and -1s. Then we say that the poset P is epsilon graded. Well, when I said graded without the epsilon, I was just basically counting the number of edges. This time we have ones and -1s as labels, so I'm just going to do the weighted sum. So I'm going to sum together all the labels I see on any maximal chain. Maximal chain in P. The sum of the labels, of the edge labels, is constant. So let me give you an example just straight. Well, every graded poset is sign graded with respect to the labeling that just puts ones everywhere. So that would be every graded poset is, say, 1 graded. And then an example of some genuine sign graded poset, which is not graded in the usual sense. Well, you can just, oops, sorry. You can just do this. And then you put a -1, for instance, here. So yeah, there are two possible maximal chains. One of them has weight 2 because there are two edges in there, but also on the left-hand side, you get 1 + 1 + 1 -1. So that's again a 2. So this thing would be sign graded, but not graded in the usual sense. Okay, and I should say that when you have such an object, when you have a sign graded poset, what is nice about those? You would need a little less than what I'm about to say, so you could actually just get a slightly more general definition. But I'm just going to state it like that because the results that come afterwards are going to use sign graded and not this more general condition. But what I want to say is that you can define a rank function. And the rank function, instead of counting stuff, is going to just do this weighted count. So in this case, if P is epsilon graded, say, we can define a rank function that I'm going to call rho. And this just assigns to each x, well, the value of the sum of the edge labels in any maximal chain that ends at x. So for instance, in the example I just showed you, you could say that this one, has rank 0, this one has rank 1, this one has rank 2, this one has rank 3, this one has rank 2 again, and the missing one has rank 1. So you can do that, well, because you have this property. If I just gave you any labeling, this might not work. And sign grade is a bit more than what you need to do this, but that's fine. Okay. So what is it that Brändén did in his paper? Like, how did he prove the gamma non-negativity? Well, he basically just finds some kind of divide and conquer strategy. So in order to examine what what W of P does, he was able to just split it as a sum of W of Q for some other posets. And the interesting part is, well, who are these other posets? And what he did was to define a saturation of any sign graded poset. So what is that? It's another sign graded poset. And I need to use a different letter also for the labeling. So I'm going to call it delta. And some conditions need to hold. Well, Q is the same as P as a set. So I've got the same number of vertices, and that's okay. Then, whenever it happens that x is smaller than y in the poset P, the same happens in Q. So basically I'm like whichever relations I got in P, I need to see them in Q as well. But I could add some, and that's what we're going to do in general. Then the rank function, remember that these things are both sign graded. They do admit rank functions, both of them. And the rank function is the same. That's one of the key parts. So up to now, so nice and good. And then comes the kind of defining property, like what makes it saturated. It should be that we cannot really add anything more to it. And that's what I'm about to write. Whenever you have two elements that differ in rank by 1, I'm going to use rho because it's the same rank function for both, then these two elements are going to be comparable in Q, even though maybe they were not in the original poset P. So this thing is called a saturation, and I can actually give you an example. Let me actually see that I don't want to use the wrong direction. So yeah, okay. So if this is my poset, and I'm gonna number it like this. Well, there are plenty of possibilities. Now, here I just mean that I have the label 1 everywhere. So there are no -1s in this particular example. But the posets Q, they're going to have also labels -1 maybe. So there is one saturation that is just taking all possible edges. Yeah, it's not going to look pretty, but you get the idea. So this one, everything is, all the edges I've added, they're just labeled by 1. But I could do many other things, and I'm just going to give you one so that we get an idea of what can happen. You could do something like this. And here I could have, well, I have 8 of these examples. I can just give you one, for instance. This would work. If you check, if I didn't mess up, of course, I didn't really change the relations that were in P. I maintained all of them. So for instance, 2 was below 6. That's still true here, even though I have to pass from 7 to 1, from 1 to 6. And the rank is the same on both sides. However, you see that, well, this thing is a bit different than what I used to have. And I have actually 8 possibilities for this one. And I could get, there are at least, I think there are 5 combinatorial types of these objects. So why do we care? Well, Brändén's result is that if you want to compute the omega polynomial, what you can do is just sum together all of these things whenever Q delta is a saturation of the original poset. And if you can do this, you have reduced the original problem of proving gamma-nonnegativity from the object you're interested in some, well, smaller sets, some smaller class of examples. And actually, there is another nice result under the correct assumptions. So if P is parity graded, whatever this means, but this is always the case when your object is sign graded. Then you actually can describe saturations. There are things that are basically anti-chains stuck together. So you have some anti-chain, then you put just ones over. I'm just going to write it down and then I'm going to describe it. where all of these AIs are anti-chains. So let's just look at that in the example. So in this example here, oops, okay. Sorry, I'm lagging a bit. Am I still here? Okay. Sorry, my connection is not great. Yeah. Okay. So in the example I'm describing here, there is an anti-chain with 3 elements, 2, 3, 4. Then everything gets connected to an anti-chain with a single element, 7, by edges that have a label 1. That's the meaning of this direct sum with a 1 below. Then the single anti-chain 7 gets connected to another 1-element anti-chain 1 by a single -1 edge. And that's the meaning of this -1 under the direct sum. And then again, I have a 3-element anti-chain, and I get all connections below. And if you think of the previous one, well, I just have a 4-element anti-chain, and above that, another 4-element anti-chain, and I get all possible connections. So I get a bipartite graph. And then, well, if you can prove both of these statements, you're done. Simply because, well, you have basically reduced the computation to understanding what happens to ordered polytopes of anti-chains. And these are hypercubes. For hypercubes, you would get Eulerian polynomials W polynomials. And for those, everything is nice. In particular, they are real-rooted. So you get they are gamma-nonnegative, and if you sum things together, you still get something gamma-nonnegative. So that's how Brändén's original proof goes. Are there any questions up to here? Okay, quickly, I'm going to give an Ehrhart theoretic interpretation of this. So I'm going to link this thing to polytopes. So if omega is a natural labeling, so remember that meant that there were no edges where you had something in the Hasse diagram where the lower vertex had a higher index than the higher vertex. So when that happens, basically, if I'm thinking of p omega partitions, I'm just getting order reversing maps, which means that, yeah, so let me write it down. P omega partitions are just order reversing maps from P to numbers that are integers greater than or equal to 1. So in particular, the omega P omega of t, this was counting those P partitions, but in this case, we are just counting order reversing maps. This happens to be the Ehrhart polynomial of a certain polytope, which is known as the order polytope. So what is that? It's just the collection of the maps from P to 0, 1, such that, well, the order is reversed. So this is a lattice polytope. It's very well studied, and its facets correspond to basically you can read a lot of information about the poset in the geometric structure of the polytope and vice versa. And this was introduced by Stanley in the 80s. So how can we tweak these so that we actually can discuss the more general case, the sign-graded case? Basically, we are not going to get full polytope, full dimensional, they're going to be full dimensional polytopes, but they're not going to be closed polytopes. I'm going to take my order polytope and I'm going to remove some facets from it. So I'm going to get some convex object, which is not a convex polytope in the usual sense, but it's still something convex where you can do the Ehrhart counting, and you get some expression. So if P is epsilon graded, again, I would need a bit less than that, but if you're interested, you can just ask me later. So you can define this new object as the convex set that consists of all those functions from P to 0, 1, so same as above, such that, well, on the one hand, I still want the order reversing business, so that's just the same as before. But then, if I have a covering relation, so if Q is just above P, and the edge label is a -1, so I get something not nice, then I just want my inequality to be strict. So basically, this is just removing some of the facets. It's basically removing the facet that corresponds to the P below Q covering relation in the Hasse diagram. And so Brändén himself actually proved, even though he was not using this way of thinking, he was just doing that purely combinatorially, that this thing, which is the H star polynomial of this new object, is palindromic and gamma non-negative. Which means that we can just go further than what we just described. We can just play the same game with these sign-graded objects. So this was the starting point for us, because we wanted to prove some equivariant version of all this business. So I know that I don't have that much time, so I'm going to give you a very brief introduction to what it means, to what this thing means. So I'm just going to give you the slogan and then describe it a bit more. So instead of doing the usual counting, what I want to do is basically taking care of symmetries of some given polytope. So I have a polytope, a finite group acts on this polytope and preserves it. So I have some group that does whatever to the lattice, and then my polytope happens to be preserved by this thing. Then I can do some more refined version of lattice point counting. Instead of just counting stuff, I can also remember how these things are permuted. And so the natural way to do this is using characters. So I'm going to give a very brief idea of what this means. So instead of using numbers, natural or integer numbers, I want to use characters of some finite group. And actually, characters would be genuine representations. In general, I would need something known as virtual characters. For those in the know, this is basically doing the Grothendieck ring of representations of G, of the group G. But we are just playing with characters because we are working over the complex numbers and the information is the same in this context. So we want to do this and get something similar to an Ehrhart series but that remembers symmetries, remembering symmetries. Okay, so how do we do that? Just a setting. I have G a finite group. P is a d-dimensional lattice polytope. Say that the lattice is Z to the D. And then, well, the formal way of writing this is that I have some affine transformations of R to the D. So I have some kind of action such that the polytope is preserved by any element. Okay, so the new object is this equivariant Ehrhart series. So, as I said before, instead of counting lattice points, in this setting, the lattice points of my given polytope, they're gonna stay the same. Well, even if I embed my polytope one dimension higher and do the usual slicing that happens with error counting, then whenever I apply an element of G, since the polytope is preserved, the lattice points just get shuffled around, which means that instead of just counting, I'm just going to consider this thing. So these IP intersections Z to the D is just the set of lattice points of the ith dilation. Then I'm going to consider how this thing gets shuffled around, and the correct way of doing that is remembering the character associated with the permutation. And so this object is not a series with natural coefficients anymore. It's a series with characters as coefficients. And from here, this should be the equivalent of what you get when you just try to count lattice points in each dilation and take the generating series. Now you want the rational version of that. There are technicalities that I'm not going to go into, but one can define something that I'm going to use. I'm going to denote by this. This would be one would like to say that this is the equivariant H star polynomial, whatever this is. This is the multiplication of this series by some polynomial that I'm not going to get into. However, this thing is not going to be a polynomial in general, it's going to be a series. A formal series. So that's a big difference with the usual case. And there are still plenty of problems on when you can actually say that this thing is a polynomial and why, and like what is really just happening under the hood. This theory is due back to Alan Stapledon, by the way. He had a paper about this in 2011, and lately he's been back about finding out what's going on. So this the idea. I know that I was not particularly, well, I didn't really go much into the details, but what I want you to know is that this thing does remember symmetries in the sense that if I take my equivariant series, this is supposed to be a row, sorry. And I evaluate that as an element G, its character, so I can just plug in G and get a number. What I get is the usual Ehrhart series of the part of the polytope that is fixed by that element. This is not a lattice polytope anymore. It's a rational polytope in general, but you do get this equality. So in this sense, you get some object that remembers at once all the fixed polytopes. And so it's like, it's a nice object to have all at once because it gives you a lot of information that you need to store separately. Okay, so I've said that in general, this thing is not going to be a polynomial, it's a series. But if this thing happens to be both palindromic and, sorry, both polynomial and palindromic, then you can do the equivariant gamma polynomial. Just playing exactly the same game as I showed you before. It's not going to be numbers, it's going to be characters, but you can just sum them and subtract them all the same. And you just get the same thing. It's just going to be a vector of characters instead of numbers. And then what is the substitution? Like I had positivity before. Now I'm going to get effectiveness. Effectiveness means that my combination of characters is just something that comes from a genuine representation. So it's a positive sum of irreducible representations. So there are no minus signs involved. So gamma non-negativity becomes gamma effectiveness in this setting. Okay, so that's the setting. I know that I'm pretty much out of time, so I'm just going to give you an idea of what we needed to do in order to prove our theorem. So I'm going to state the theorem and just say a few words. So the theorem just says that if P is graded, so notice that even though I described all of this in the more general setting, the statement itself only works for graded posets, or at least that's what we were able to do. We don't know exactly how to extend this. And you have a subgroup of the automorphism group of the poset, then P is gamma effective with respect to this action. So remember, I'm just gonna go back a little. Here we got the formula by Brändén, sorry. And so we would like to do the same. What is the problem? The problem is that if you just act by an element of G that preserves the labeling, so in this case, just any element of the automorphisms, and you act on a saturation, that is not going to be preserved. You're going to get some other saturation. However, the set of saturations is going to be invariant. So you need to do some kind of, you need to consider all saturations at once and see what happens. And then, well, there is a very ugly formula that you can write down that basically says that there is a kind of miracle that happens. So I'm just going to write it down, not because I want you to look at that, but because I want to say in words what's going on. So here I have the H star polynomial of my original poset P. Here I'm assuming that P is epsilon graded. And here I'm going to get some combination of H star polynomials of the saturations, but not with respect to G, but with respect to their own automorphism group. And then I get a bunch of induced and restricted representations. So pretty much what's happening here, the miracle that is happening here, is that even though here I'm working on with G and here I'm working with some other group, I can still find a way to relate the two expressions. And these Q1, QK are just representatives. For the orbits. Okay, so that's one ingredient. The second ingredient, I'm not going to write it down because I'm almost out of time. The second ingredient is basically the same as what Brändén did. So he was able to go back at like to hypercubes, and we can pretty much play the same game. So that's a part that is kind of similar to what he did. So we can actually describe, this sum is going to tell us that if you are really interested in the gamma positivity of H star P, you can just look at saturations in this sense, just all at once, but you can do it. And then saturations are going to be basically linked to hypercubes. So the question becomes whether if you get the symmetric group acting on some anti-chain, whether you get something gamma non-negative or not. So basically the equivalent of the Eulerian poset, the Eulerian polynomials you got before. And that is known, but has not been known for such a long time. It's a 2017 result by Athanasiadis. So basically, these things I wrote just gives you the reduction to saturations. And then for saturations, you can actually go all the way back to hypercubes, and those are going to be effective by work of Athanasiadis and then by Shareshan and Vax and other people. So yeah, I think that's pretty much what I wanted to say. So I'll stop here and thank you.
Thanks, Alessio.